It's lesson 3.1.1. We're in chapter 3, which is equations and inequalities, and this lesson we're going to go over various strategies for solving equations. So today's objective, you guys are going to be able to visualize what it means to solve equations, and then we're going to examine both the algebraic and graphical strategies in solving equations. Now, amongst the algebraic strategies, we're going to be looking at linear, quadratic, absolute value, rational, square root, and then U-substitution type equations. So first, what we're going to do is we're going to examine what it means for us to be able to solve an equation graphically. Now, from a technical perspective, any equation can be broken down into two functions. So this equation that I have here, x squared equals 4, I can go ahead and break that into two separate functions. The first function, f of x equals x squared, and then the next is going to be g of x equals 4. So each side of that equation is going to equal its own function. Then, once I break it down, we first want to examine what is being asked when you set those two functions equal to each other. And that's where they intersect. And so, where does this x squared and this 4, where do these two graphs intersect with each other? And so looking at our graph here, I graphed y equals x squared right here, and I graphed y equals 4 right here. And if you notice, they intersect at these 2 points here, and so I have these 2 points. Now, because in my representation here, I'm looking for x, I want to look at the x values here. So -2 and +2 are going to be my answers. Now sometimes, and we're going to go into how to graph them a little bit more in the next lesson. This lesson we're going to focus a little bit more on the algebra part, but sometimes it's much easier for us to be able to solve an equation algebraically. There may not be a graphing calculator available, maybe it takes too long, sometimes it actually is a little quicker. And so we're going to review the different strategies that are used to be able to solve the different types of equations that we're going to see. So the first type of equation that you've seen probably is a linear equation. And we can tell because the highest exponent is 1. And so the strategy here is we want to get the variable to one side and the constant to the other. So in this instance, I'm going to subtract both sides by 2x, and I'm going to subtract both sides by 4. The 2x's will cancel out here, the 4 and the -4 will cancel out here, and so I'll end up getting 3x minus 2x is x, and then -9. So that right there is going to be my solution. On this one here, there's two ways to go about this. I could distribute the 3 if I wanted, or I can divide both sides by 3 because they're factors, and so the factors of 3 would cancel out. And so then subtract the 2 on both sides, and so I'm going to get x is -1. Now let's examine that graphically. So notice I got -9, and I got 1. I just did y equals this graph, y equals this graph, and so we have our two graphs shown, and so my solution there is -9. Likewise here, the solution here is 1. Now when we have a quadratic equation, we can tell because the highest exponent is a 2. So in this instance, it's 2, or 2, because when I multiply this out, if I were to distribute this out, right, x plus 1 times x plus 1, x times x is going to give me x squared. So the strategy is, well, there's kind of like two strategies that go with this. The first, we call it the square roots method. And essentially, if we're able to get a perfect square by itself where it's not awkward, we can go ahead and like square root both sides to solve. So, and what I mean by that, and I'll clarify that as I go over both of these. But in this instance here, I have x plus 1 squared. It's really easy for me to just subtract the 2, and now that x plus 1 squared, that square part is by itself. And so for us to get rid of that square, we take the square root to both sides, and so the square root and the square are going to cancel out. And so then I'm going to get x plus 1 equals plus or minus 2. I could break those up since it's plus or minus, that's going to be two different equations. And I could subtract 1 on both sides, subtract 1 on both sides, and you're going to get x equals 1 and -3. Now in this example here, the square roots method is not going to be effective. And the reason being is if I were to get this x squared by itself, and I have my 7x on this side, well, when I take the square root to get rid of it, I'm going to have an x inside the square root. That's not going to be very helpful. So the other means for us to do it is to set it equal to 0, and then from here, we can either use the factoring method or the quadratic formula. And so this can actually factor, and so the factors of 12 is 3 and 4, add to 7. Set each one equal to 0, and so you get x is negative 3 and x is negative 4. And so those are going to be my solutions here. And so let's compare them. Let's look at this first one, 1 and negative 3. See, it crosses at 1, so there's my x value, there's negative 3. And then we said negative 3 and negative 4. And so we have negative 3 and we have negative 4. Absolute value. The way that we recognize this is that there's an actual absolute value. And the way for us to be able to solve this one is we're going to use this definition here. And the definition of any absolute value says that when the absolute value part's by itself and we know it equals some positive number, I'm allowed to assume that whatever's inside that absolute value is positive, or whatever's inside that absolute value is negative. And so I can make those two separate statements. And so I'm going to have to, since the absolute value part is by itself, I'm going to break that up into these two equations. One is the positive, right, because it's a positive x plus 3, and then a negative, so a negative x plus 3. And then you solve each of those statements individually. So I'm going to subtract 3 on both sides, and I get x is 1. That negative will be divided on both sides, or you can go through and you can distribute it. And then I can subtract 3 on both sides, and so I'm going to get x equals negative 7. Now we can check our work to verify this. If I plug in 1 plus 3, absolute value 4 is 4. If I plug in negative 7 plus 3 is negative 4, the absolute value negative 4 is 4. Now on this one, the same thing, we're going to be able to use that definition, but what we want to do is we want to make sure that the absolute value is isolated. So I want to get the absolute value part by itself. So to do that, I'm going to subtract 4 on both sides. And then I can divide both sides by 2. And so since they're factors of 2, those are going to cancel out. Now that the absolute value part is by itself, then we can use this definition. So I assume that whatever's inside the absolute value is both positive and negative. So whatever's inside the absolute value is both positive and negative. And so I solve for each one. So add 6 to both sides. I can distribute the negative, or I can divide both sides by the negative, then add 6 to both sides, and so I'm going to get x equals 4. So let's check our answers. We said 1 and negative 7 for this one. There we go. We got 1, and we got negative 7. And then on this one here, we had 8 and 4. And so we have 8, and we have 4. So now we're going to look at rational functions. Now, the way that we know a rational function is rational is the fact that there exists fractions. Mainly, there is values in the denominator that we have to get rid of. Now, I'm not going to go through all of it and how we solve them, but I'm going to go through the idea of how we can go through and manipulate it into a form in which you would have to use other ways to solve it. Now, the strategy here is we have to get rid of the denominator. Now, for us to get rid of the denominator, what we need to do is we need to multiply everything by what's inside the denominator. So in this instance, because I have an x plus 1 in the denominator, I want to multiply both sides by x plus 1. Because multiplying and division, they're inverse operations, and so they're going to cancel out. And so I'm going to get 2x plus 17, and that's going to equal this x plus 5 times x plus 1. Now this is all FOIL, right? I'm going to have to distribute this through, and then ... go ahead and solve. It's going to be quadratic, and so I would use the quadratic means to solve it. Same thing over here on this side. Well, I have an x in the denominator, so I multiply both sides by x. And so now that the x's, those will cancel out, and so I'm going to get 2 equals x squared, because x times x is x squared over 5x plus 12. Now I need to get rid of that 5x plus 12. So I'm going to multiply both sides by 5x plus 12. So they're going to cancel out there. And then so I'm going to get 2 times 5x plus 12 equals x squared. And so, you know, once again, because that's an x squared, that means it's quadratic. I'm going to have to solve that with a quadratic means. And this process can work with almost anything. I mean, I could have 1 over 2 plus 1 over 3x equals 1 over 5. And just one by one, you know, this is like a third example, I can go through and just by multiplying by every little thing in the denominator, I can get rid of it. And so I can multiply everything by 2. And so they'll cancel out here. And so I'm going to get 1 plus 2 over 3x, because nothing cancels out, equals 2 over 5. Actually, you know what? I'm going to change the original problem. I'm going to put an x there. So then there's going to be x there. Just so we can see how it's going to do something else. And so now I have a 3x in the denominator. So I can multiply everything by 3x. Now I need to reduce everything. Well, right here, nothing reduces, so I still have 3x. Here, the 3's reduce and the x's reduce. And so I'm going to get plus 2 equals, and then only on this side, the x's are the only thing that reduce. So I'm going to get 6 over 5. And so now I got to get rid of the 5, so I'm going to multiply everything by 5. So you multiply each term by 5. Each term. And so now the 5's will cancel out, and so I'm going to get 15x plus 10 equals 6. And then you just solve from there. Now, just like with any equation, I can also graph them. And so here are the actual solutions to these equations here. So if you wanted to go through and finish them, -6 and 2. And then for this one, it'll be -2 and +12. So if you want to go ahead and finish them and check it, go for it. But those are going to be our solutions. Now we have the square roots method. Now the way that the square roots method works is, well, there has to be a square root. But just like with the absolute value, we want to try and get that square root by itself, or try and get a square root by itself. And so the way that we would do that is we would square both sides right when it's by itself. So in this instance here, I want to get rid of that 2, so I can divide both sides by 2. And so then they're going to cancel out there. And so now I have the square root of x plus 2 equals 2. And then now I could square both sides, because that'll cancel out with the square root. And then I get x plus 2 equals 4. Subtract 2 on both sides, and I get x equals 2. Now there is something I want to talk to you about. In math, we've gone over a domain. And domain, whereas everything was defined, right? It's where like the x values exist when it comes to an xy graph. Now there are certain equations that have domain restrictions. Rational is one of them. So in the previous equation, technically we should have done this step, but I wanted to save talking about it to, you know, this equation. So we have rational, we have radical, and then logarithmic. Those are our 3 algebraic equations. And then there's going to be a few trigonometric equations that are going to have the same premise, but we're just going to stick with the 2 right now because we haven't talked about logs. So just rational and just square root. But with a square root, there's a restriction to our domain. We can't have a negative inside of it. It's not real. It's going to be a non-real answer. For the rational, you can't divide by 0 because it's undefined. And so you have to make sure that the solution that you get using algebra works within the domain. So you have to plug it back in and check it. And the main reason is because as we're going through and we're doing algebra, sometimes there might be a logical step we're missing. Like we're doing something that we're not supposed to be doing. And sometimes it's really difficult to see. And so that's why we have to check our answers. So I should take this 2 and plug it back in and see if it works. So 2 plus 2 is 4. Square root of 4 is 2. 2 times 2, that gives me 4. We're good. So now let's try this next one. Remember, at the end, we're going to have to check our solution. So to get rid of that plus 6, I'm going to subtract 6 on both sides. And then divide both sides by 3. And now to get rid of the square root, I can square both sides. And so I'm going to get x minus 1 equals 64. Add 1 to both sides, and I get x is 65. So now I need to check my answer. So I'm going to take that 65, and I'm going to plug it right back in. And so 65 minus 1, that gives me 64. Square root of 64 is 8. 3 times 8 is 24. 24 plus 6, uh-oh, those don't equal. So 65 is not one of my solutions. It can't be one of my solutions. So there is no solution. Now here's the logical step we missed. So let's back it up real quick. How can the square root of something equal a negative number? It can't. And so we missed it just using regular algebra to solve. And so that is the reason why we need to check our answer. Is because this solution that we have here is outside the domain. It doesn't make sense. It's no solution. And so that's why it won't work. Now visually, all that means is that they don't intersect. And so as you can see here, this graph and this graph, they don't intersect at all, which is the reason why we got no solution. Over here, 2. That verifies it. Now another form of no real solution is going to be if we have imaginary numbers. So sometimes the same thing can happen with quadratic. And so if we have an imaginary number, it means that they won't intersect. All right, so now we're going to examine quadratic type equations, and this is going to be the last new thing. So this should be a totally new thing, something you've never seen before. Now the reason why we call it a quadratic type equation is because we're able to transform this polynomial equation into a quadratic equation by using some sort of substitution, which is why we call it quadratic type. So here's our first example here. So what we're going to do is we have to rewrite this equation as a quote-unquote quadratic equation, because if we can do that, then we're going to be able to solve for it. And so we're going to try and figure out, okay, how can I rewrite this as a quadratic equation, basically? And so sometimes what helps with that is if you say, well, if I let u, or if any variable, equal a certain value that exists already in this equation, it might be able to help. So now in this instance, if I said u is x squared, well here I have 2x squareds, right? So technically that means if I said x squared is u, that's just u, and then that x squared right there replaces directly with u. And so now it's a quadratic equation. And so because I transformed this into a quadratic equation, all the properties and rules of a quadratic equation now apply. I can factor it, I can use the quadratic formula, etc., etc. And so let's factor it, because it's a quadratic equation, and I think this factors. So this will factor into u plus 3, u plus 2, and so that equals 0. And so setting each one equal to 0 and solving, you're going to get u equals -3 and u equals -2. But I'm not solving for u. Remember, we're solving for x, so I can re-plug in x squared. And so now taking the square root to both sides, I'm going to get x equals plus or minus root 3i, and x equals plus or minus root 2i. Because there's a negative inside, so that's why it becomes imaginary. And so those right there would be our solutions. They're not real solutions, but there are solutions. So here's what I did. The first step, I substituted u in as a value within this equation so that it turns it into a quadratic equation. Now in this instance, I said u is x squared. Now here's a hint. Typically, it's always going to be this b value right here. And so I said u equals that, no, b value, I'm sorry, that's a b value, it's the value next to b. And so I said u equals x squared. And so now I factored it, so I just solved the variable, got it by itself. Step 3, I resubstituted it. So we are not solving for u, we're solving for x, so that's why I resubstituted x squared in. And then I continue to solve, and that's how I got x by itself. So let's look at another one. So this one already kind of looks like a quadratic equation, but my first step is I'm going to substitute u in for a value. Remember, it's always typically the value next to b, so let's see if it works. So if I say that that's going to be u, so now I'm going to get u squared minus 2u minus 3 equals 0. Yay, it works. So now I need to solve. So get u by itself. Well, it looks this one might factor, so let's check that. So u and u factors of 3 that add to 2, so 3 and 1, negative 3 plus 1. So I'm going to get u equals 3 and u equals negative 1 when I set each one equal to 0. Well, we're not solving for u, so I need to resubstitute back in. So that's step 3. So x minus 3 equals 3, and x minus 3 equals negative 1. And now I continue to solve. So add 3 to both sides. X equals 6. Add 3 to both sides. X equals 2. Let's look at one more, and instead of going through and solving it, I'm just going to do the substitution part, just so we make sure that we understand the U-substitution, because I'm trusting that you guys know how to solve quadratic equations. So this is what our u is going to be. We're going to say u equals x to the 4th. Let's test it out. Because here, there's 2x to the 4ths, so that should work. So I get u squared minus 7u minus 18 equals 0. Cool, it worked out. And so dot dot dot, you would have to use, since it's a quadratic equation, you'd have to use a quadratic means to solve. All right, so let's close this lesson. What did we learn today? Well, we examined algebraic and graphical strategies in solving equations. So on almost every single one of those equations that we had, we went through and we solved them both linear, quadratic, absolute value, took square root, we did some rational, we looked at that U-substitution, and then on most of those we actually decided to put them to graphs and see what they looked like graphically and compare the solutions there. And how do we visualize an equation by graphing? Well, to visualize an equation by graphing, we separate each side of the equal sign. We allow each one being a function. We put it into a graphing calculator like Desmos and see where they intersect, and then the x value is our solution. This does conclude our lesson. If you do have any questions, please leave them in the comments.